and welcome to today's lecture on the periodic table. What we are going to be working with today is we're going to be talking about some of the trends that are going on with this periodic table. And I'm going to kind of show you guys some things to think about while you're looking at the periodic table. And these can end up being shortcuts for if you need to go ahead and figure out how some certain things are going to end up bonding or whether certain things will bond. And we're going to be covering three main topics here. And the three main topics that we're going to be covering are going to be size, ionization energy, and electron affinity. Okay. And the first one here, size, this is going to be the atomic radius, and this is typically how we measure it. We say that it's the atomic radius. And this is going to be determined by the number of electron energy levels and the number of protons. So we're going to go ahead and start here and work with size first. Okay, so we're going to go ahead and move over here to paint. And the reason that we're doing this in paint instead of something else is because it's really easier to kind of draw and elucidate this with drawings instead. And what we're going to do is we're going to go ahead and start with an atom. And we're going to say that this atom has a nucleus, and inside this nucleus that it has 9 protons. Okay, so inside this nucleus we have 9 protons. Now, these 9 protons, what they're doing is they're essentially giving out like this energy force that's trying to pull in electrons. Okay, and electrons, they're kind of wiry buggers. Okay, so they have all sorts of energy, they're moving about at the speed of light, and this nucleus is trying to pull on those electrons. Alright, and as it's pulling, it is likely to catch at least 1 or 2 of them. Well, it's going to be able to catch 9 of them total. So what we're going to do is we're going to go ahead and draw where the electrons would go here for this one. And it's going to start, it's going to have a first energy level. And the first energy level is going to be fairly close to the center because that's where that's where the most pull is from. And the first energy level can only hold 2 electrons. Okay? And we can go ahead and also verify this. We can go ahead and go back and I'll show you what's going on here. Is that this first energy level, which is this one right here, it has 1, 2. So that's the most amount that it can hold. That's the most amount of electrons. Okay? Then we're going to have a second energy level. Okay? And this second energy level is going to have to go outside of the first energy level. Okay, and we forgot to switch colors. So this second energy level is going to go outside this first energy level. And it's going to have 1, 2, 3, 4, 5, 6, 7. Okay? And so this is going to be this particular atom, and because it has these 2 energy levels, its radius is going to be defined by the outer energy level, or how big that outer energy level is. Now, I want you to imagine that this atom right here is actually having lines of force that's trying to pull in on this energy level. Okay? And we have 5, 6, 7, 8, 9. And these lines of force are coming from the nucleus, and it's pulling on here. Okay? If we were to go ahead and take another atom, we could go ahead and mess with the number of lines of force. Okay? So let's go ahead and say that instead of 9 lines of force, let's go ahead and add another line of force. Okay? So we're going to go ahead and say that we have 10 lines of force. Now, 9 lines of force pulled everything in this close. 10 lines of force is actually going to pull it in even closer. Okay? And the idea behind this one is that because there's more protons and it's pulling on the same energy level, that it actually pulls the energy level closer to the center of the atom. And look, we can go ahead and say here, all right, this one has less lines of force, this one has more, and this one ends up being smaller. Okay, so this one's smaller because it has more protons that are pulling on these energy levels. Okay, and that's what we want to go ahead and get here. So it's determined by the number of protons. Now, the second thing that defines this is going to be the number of energy levels. Okay? So what we're going to do is we're going to go ahead and we'll get rid of this one right here, because the other one I think I like the drawing more. Okay? And this one, notice this has 2 different energy levels, and now at this point the second energy level is filled. Okay? So what's going to happen now once we add in a third energy level? Well, that third energy level is going to end up being larger in order to encompass this last one. Okay? And once it gets larger, it ends up having kind of like a shield effect that's going on here. So I want you to imagine that this energy level, this third one, is kind of being shielded from this nucleus right here by these other outer energy levels. Okay? And so every time that you end up getting an extra energy level, so if we added one more electron here, it ends up being a much larger energy level until we start to add in more protons to pull on that energy level a little bit more. Okay? So every time that we get a new energy level, we're going to increase in size by quite a lot because it's being shielded from the main body of electrons by the lower energy levels, and because it has to go around all the other energy levels. Okay? So that's what's going on with size in terms of energy levels and protons. Now let's go ahead and see how it works on the periodic table itself. So this is the periodic table, and right now we have it in the IUPAC setting. And I want you to notice that the first energy level is this row right here, and there's only 2. The second energy level has a total of 8 in it. The third energy level has 8, and then it goes and gets bigger. This one has a total of 18. And we're going to go ahead and go to the calculated radius tab. Okay? And we're going to go ahead and go through, and we're going to explore this one here. So our first energy level, we have 1 proton and 1 energy level. And we start at 53 p.m. We move on to the next one, which is helium, which has 2 protons pulling on that single energy level, and we end up getting 31 pm. Okay, so that follows what we expected, that as we go up in terms of the number of protons that are interacting with an energy level, it's going to pull that energy level in closer. Now, if we go to lithium, which is number 3, we would expect that that radius is going to get bigger. Okay, so we're going to go to lithium now, and we see that it has ballooned out to 167 pm. Okay, so it got really big because now it has a whole new energy level, but there's only 3 protons pulling on that energy level. Then as we go forward, we see that it gets smaller. Okay, beryllium has 4 protons pulling on the 2 energy levels. And so it gets smaller. It goes from 167 to 112. And then it gets to 87, then 67, 56, 48, 42, then finally to 38. Okay? So we have this trend that as you go across a row or across something that has the same energy levels, that it gets smaller. And then as you go down and increase the number of energy levels, it gets larger. So that means that even though we don't have the actual radius for francium figured out, we would expect that francium right here would have a larger size than cesium. Okay? And so that's what we're talking about with size. Now, next, we're going to go ahead and talk about ionization energy. And ionization energy is likely a new term for you. However, thinking about it in terms of thinking about this concept of atoms in terms of the size of the atom is probably going to be really, really useful for you. And in ionization energy, the amount of energy, or the definition for ionization energy, is the amount of energy needed to strip an electron from an atom. So let's go ahead and go back to our example here. And we're going to go ahead and go backwards here and say that we have this one right here, and this is neon. And it's a pretty small, compact atom. And we're going to go ahead and draw for it a twin. And we're going to draw sodium. Okay? And sodium has a nucleus. It's just a little bit bigger. Oh, let's hit the right color. And this is 11. And we need to draw the energy levels, so we're going to draw in, oopsies. We're going to go ahead and draw the first energy level, which is going to be really, really close there to the nucleus because it's pulling on those electrons pretty tight. We'll go ahead and draw in our electrons, 1, 2. And then we're going to draw in that second energy level. And that second energy level is going to be really tight as well. Oh. And we'll draw in our electrons, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and now we have 10 electrons around here. And we have to draw in one last energy level. And this one is really big and far out here. And it only has 1. Made this just a little bit too big, so we're going to go ahead and smaller. All right. Now, we're talking about ionization energy. Okay? Ionization energy says that we give energy to these electrons, hoping that we're going to be able to get them to break away from their nucleus. Now, which one of these atoms seems like there's an electron that has a head start? Okay? It's going to be this one here. So the larger that it is, the more likely you're going to be able to strip an electron off of there. Because if you think about it, this one's already close to the edge. All of these are being really well held tight there. Whereas this one is really tightly held to the edge. So our idea of ionization energy is going to be inversely related to size, because the larger the size, the less pull there is on that electron, and there's less of a hold on it here. So we're going to go back to our periodic table here, and we notice that right here, this is our energy, this is the size area, okay? So what we're going to expect is that this size area is going to have a really low amount of energy. And this area, where the size is really small, we're going to expect to see that it has a high first ionization energy, okay? And we're going to hopefully be able to see that with the coloring here, because right here it's dark, it has a large size, okay? And the coloring is terrible, just terrible on here, okay? But let's go ahead and take a look. Let's go ahead and test our hypothesis. So here we said that cesium should have a really low first ionization energy. And as you could see from this graph, it actually tells it to us, and it says that it's 375 kilojoules, okay? Now we can go ahead and go to fluorine, which is a lot smaller, and it's on our small end, and we see that that has jumped up to 1,681 kilojoules. So it has a lot more energy to remove that electron from it, okay? And let's go ahead and use the exact example that we had in our image, where we had 10 and 11, okay? 10 is neon, and neon has a first ionization energy of 2,080, okay? So it's 2,080. It takes a lot of energy to remove that electron from it. However, if we go over to sodium, sodium only requires 495, so it requires only about 500. It requires 4 times less energy to remove it because it's so far away, okay? So that's what I want you to get out of this, that the larger that the atom is, the less ionization energy it takes, or the less energy it takes to remove that electron. Now the next one that we have is called electron affinity, and I know this should be a new term for a lot of people, and it's going to be the change in energy from a neutral atom to a negatively charged atom when an electron is added to it, okay? And what that means is it's basically how well an atom is going to be at stealing and holding onto another electron, okay? And electron affinity is just our way of measuring that based off of how much energy is released once we have that electron grabbed onto. So I want to go back to our picture right here, and I want you to go ahead and think, all right, which one of these is going to be able to hold on to an extra electron better? The one that has the really large size here, or the one that's a little bit smaller? And actually, we need to go ahead and make a quick change on this one right here. And we're going to go ahead and change it to essentially B plus 9. And we're going to remove an electron. Okay. So between this one and this one now, which one of these is more likely to grab onto an electron? Which one, if you add an electron to it, will hold onto it better than the other one? So this one, if we add an electron to this one right here, it would go, oh, let's go ahead and put it right here. Okay, it's not being held on very well. Whereas this one that has a total of 9, that one's pretty strongly held in there. Both of them have an extra electron and they have this, -1 charge to it. But this one, because it's so much closer to the nucleus, it's going to be held on so much tighter to that nucleus. And that's the same concept really for most of this electron affinity. Okay. And that the smaller it is, the more likely that it's going to be able to hold on to an extra electron. Now, one thing that I want you to go ahead and note is that the noble gases right here all have an electron affinity of 0. And the reason that these have an electron affinity of 0 is because these ones are already all the way filled, okay? So this one is an example of neon, and notice that it's all the way filled, which means that it really doesn't want to grab another electron, which is why these ones have no electron affinity whatsoever, okay? And what you'll notice is that for a general rule, the electron affinity is going to go increase and go towards the right, just like we saw with that ionization energy, except that it's going to stop at fluorine instead of at the noble gases here, okay? That right there is going to be the last thing that we covered with this one right here. The 3 terms that I want you to make sure that you're able to trace on the periodic table are size, ionization energy, and electron affinity. One note on electron affinity is that this term is also used for the idea of electronegativity. And electronegativity, when spelled right, it is spelled right. And electronegativity is essentially the same thing as electron affinity. However, electron affinity is using actual measurements for it instead of a scale-based system, which is more common in lower-level chemistry courses. Okay, so if you see these two, just know that they're related. This one has a measurement attached to it, and this one is relative to each other. Okay, and that's going to close out this video for today.